Hello and welcome to EE323, Lecture 8. Today I'll be introducing the concept of amplifiers. We'll be introduce the topic, talk about some amplifier specifications today, and you can find this relevant information in the book in section 1.4. All right, so let's get started. This amplifier section will have 4 lectures in total. We'll start out today with the motivation and describing amplifiers. We'll move on in later lectures, talk more about transfer characteristics and efficiency, amplifier circuit models. We'll talk about what happens when you put more than one amplifier together, that is, you cascade amplifiers. And finally, we'll talk about the amplifier response as a function of frequency. We have some time-dependent input with a varying frequency, and we'll try to figure out what happens as you increase the frequency. Okay, next slide. So amplifiers, generally, what's the purpose of an amplifier? The purpose is to enlarge a signal, typically often a voltage signal. It takes some small input and it will convert it to a larger output signal. Amplifiers are used all over the place in electrical engineering, in circuits, and on integrated circuits and discrete circuits, on circuit boards. Amplifiers are very, very common circuits. So let's talk about an example here. An example would be audio speakers. They clearly need to amplify the signal to drive the amplifier. So one example might be if you have an antenna for a radio, for example, like you would have on a cell phone. The antenna picks up the signal of interest. These radio waves typically have a very low voltage associated with them. They're typically very small signals. You would then use a voltage amplifier to boost the voltage. And then you'd actually need a separate type of amplifier to drive the speakers. And this might be called a power amp or a current amp. And the challenge with driving the speakers is that the speakers have a low impedance and because of this, you need a certain special kind of amplifier to be able to drive that low impedance. In general, low impedance is difficult to drive, and if we try to understand why we might call this a current amplifier, and the reason is that for a low impedance, right, they're going to take a high current to drive that for a particular voltage. So that's why we might think about this more as a current amplifier. Another example would be a CD. So if we have a CD, it has some optical detector on it. Again, the output of that is typically a low voltage. And if you wanted to play this through speakers, we'd need to go through a similar stage of a voltage amp, followed by a power or current amp, and finally to the speakers. All right, let's talk about some amplifier requirements. Obviously, we need our amplifier to amplify, right? And so if we think about what sort of requirements or characteristics that might happen, that might require, the first thing we need is a stable gain, right? This is to amplify our signal. We want it to be larger at the output, or we want it to be stable. We want it to not change over time. Second thing we want turns out to be something called linearity, and that is if we put an input signal in, we want an amplified signal at the output, and we do not want it to be distorted. So the ideal amplifier here has some input, we call it Vi of t, going through our amplifier A, and our output then is going to be the gain of our amplifier A times the input. Now, where A is the amplifier gain, if we have a perfectly linear amplifier, we see just a scaled version of the output. However, if we have some nonlinearity, then for an audio signal, for example, we're going to get distortion. We might have harmonics, and this is going to result in distortion, and the audio signal output would not sound the same as you expected. And this happens from nonlinearity in the amplifier. So we'll look at a data sheet in a second where it actually specifies what the linearity of the amplifier is. So if what we're going for, if the goal here is to have a linear amplifier, right, That's what we're trying to do. What this really means is that if we have some input signal here, some sinusoidal input, and we put it into a perfectly linear amplifier A, then the output is just going to be the same frequency. We're going to have the same frequency sinusoid, but the amplitude of our output signal is going to be changed. So the frequency doesn't change, and in fact we don't add any new frequency components if our amplifier is perfectly linear. And for a lot of this course we're going to assume that our amplifiers are linear, but we'll have to make clear that we're stating that assumption. What would an example be of nonlinear amplification? One example might be if you're listening to music in your car. At low volume, it's fairly linear, and the audio sounds pretty good. But if you turn it up really high, the amplifier starts to clip. We'll talk about what that means in a second, and that means distortion, and you can hear the audio changing, and you can actually hear the distortion in the signal. So that would be one example of an amplifier going from relatively linear behavior to nonlinear behavior. All right, let me give you some examples here of linear amplification. So in this case, we have a sinusoid coming in. The output of that sinusoid will look just like a scaled version. Again, the frequency doesn't change, but the amplitude of the sinusoid does change. Another example would be if we have a triangle wave. Again, the period of the triangle wave doesn't change, just the amplitude of the triangle changes. And finally, if we have some random signal coming in, it's the amplitude of the random signal going out that changes if we have linear amplification, and that is no distortion to our signals. All right, how do we describe nonlinear amplification? In practice, all amplifiers are nonlinear. Sometimes the nonlinearity is small enough that we can ignore it. Depends on the application. But typically, if we have nonlinear amplification, it's described by a power series. And you can see this first term here is the linear term. So this is the linear term of our amplification. And then we have the higher order terms here. These are the higher order terms. Higher order terms, and these lead to harmonics and distortion. So what you can see is if our input were sinusoidal, for example, we'd have a sinusoid squared, which, if you remember some of your trig identities, just results in new frequencies being generated. And those are the sinusoid, those are the harmonics that we're talking about. And so if you look at a data sheet, for example, right? Here's an example of a data sheet for an amplifier. This is a 2-watt stereo audio amplifier. You can see they specify here ultra low distortion, and it talks about the total THD, which is the total harmonic distortion plus noise, being 0.05%. And that basically means you add up all these other terms here, how large they are compared to your linear term. So you want those other terms to be small compared to your linear term, and that if you sum all those other terms up and you add the noise generated by your amplifier, you get the total harmonic distortion plus the noise. All right, so let's move on and talk about how we describe amplifiers. What are the models we typically use? The most general case is we use something called a 2-port model, or 2-port amplifier circuit symbol, and 2 ports because we have an input with 2 ports and an output with 2 ports. While this is the most general case, it can also be the most challenging mathematically to work with. And if we can simplify the circuit and still keep some of the accuracy, then that's a good idea. An example of a simplified circuit might be grounding one of the inputs and one of the outputs. So this is called a grounded model. Here we still have 2 inputs, but we ground one. And if we want to further simplify this, we can actually just have an amplifier with one input and one output. This is the most simplified version and lends itself to the most inaccuracy as well. So it depends on the application if we need a two-port, a grounded model, or a simplified one-port model. All right, so how do we describe gain of an amplifier? What does that mean and how do we describe it? So let's look at this example amplifier here. We have some voltage in and some voltage out. So if this were a linear amplifier, we can plot V out as a function of V in, and you can see that the slope of this line, this is a linear, and that implies linear amplification, and the slope is the voltage gain. So we can write that the voltage gain AV is equal to V out over V in. That describes the voltage gain, or the slope of our amplifier, the slope of the transfer characteristic. We can also think about current gain of amplifiers, and the current gain is defined as the output current over the input current. And we can also think about the power gain of amplifiers, and this would be written as AP, and that's going to be written, described by the voltage gain times the current gain, which would equal V out times I out divided by V in times I in. In terms of units, the units we typically use are decibels or dB. I would say this is more than sometimes, but usually dB is used to describe the gain. So the definition of dB for voltage or current gain, the definition of gain is 20 log times the absolute value of the voltage or current gain, and this would be the gain in dB. For power gain, we use 10 log times the power gain, and that would give us our gain in dB. Something that comes up frequently is this concept of 0 dB, and what does 0 dB indicate? Well, this indicates a gain of 1, and why is that? Well, because log of 1 is equal to 0, and therefore 20 log of 1 is also equal to 0. So if we have a gain of 1, that means 0 dB. So if you hear the amplifier has at 1.0 dB of gain, just unity gain or gain of 1. Next question is, what does negative dB indicate? And this means a gain of less than 1. For example, if we have an amplifier that has a gain of 1/10, we would say in dB this would be 20 log of 1/10, which would equal 20 log of 10 to the minus 1, which would equal minus 20 log 10, which would equal minus 20 dB. So in this case, we have a gain of 1/10 or 0.1, and that corresponds to minus 20 dB of gain. All right, let's talk about some more examples here. Let's do a quick example of a power amplifier. The input to our power amplifier is 1 milliwatt. We have a power gain of 100. What would the output be? Well, P out would just be AP times P in, which would be 100 times 1 milliwatt, which would be 100 milliwatts. We can convert this to dB, and we'd say that our power gain is 10 log of AP, which would be 10 log of 100, which would be 20 dB of power gain. So AP would equal 20 dB. All right, now let's talk about the actual power inside the amplifier. What's happening inside the amplifier? And how do we model it? And how do we think about it? In the previous slide, we talked about an amplifier that had some 1 milliwatt coming in and 100 milliwatts going out. Where does that power actually come from? Are we violating some law of thermodynamics in our model there? In fact, we're not. And the reason is that we often just don't draw it quite accurately. And just to make it faster and easier to draw, if we were to draw the amplifier more accurately, we would include a positive voltage supply and a negative voltage supply. The negative voltage supply is often ground, but it could be a negative voltage as well. And so we have a DC power supply for the positive supply and for the negative supply. Now, the power that's going, this new power, this 100 milliwatts that we talked about in the previous example, that power is actually coming from the DC power supply. So we're not magically making up any power, it's coming from the DC power supply. So if we're to talk about the power dissipation, the DC power dissipation, it's V1, I1, where V1 is the positive DC supply and I1 is the current coming out of that supply, and V2 and I2 are the current going into the DC supply, V2, and the voltage associated with the negative supply. So that would be the DC power. And if we want to talk about the conservation of power here, then our sort of input power, we have our input voltage along with our DC power, and that must equal the power that's going to be delivered to the load, right? That's PL, and the power that's dissipated elsewhere in the circuit. So these things have to add up so that we don't violate any law of thermodynamics. And when we talk about amplifier efficiency, we typically describe this as the power delivered to the load divided by the DC power supplied by the power supplies, and multiply that by 100 to get percent. Depending on the linearity requirements, this efficiency can be anywhere from 10 or 15% for very inefficient amplifiers, but have difficult specs to meet typically. And there are some amplifiers that can get as high as 60 or 70%, depending on the application. In this calculation here, this efficiency, we typically neglect the input power, and that's because often the input power is small compared to the output power. Like, for example, on the previous slide, the input power was 1 milliwatt and the output power was 100 milliwatts, so 1 is small compared to 100. Graphically, it also helps to look at the gain of our amplifiers graphically, and this is a figure from your book. This is figure 1.14 from the book. And there's a lot going on here. Let's try to break this down. First of all, we're plotting V out as a function of Vn. Right? So we have an amplifier, and this is V out as a function of Vn. Right, so this might look like this. So we have Vn and V out. And this is a somewhat simplified model, but still very useful. We have some amplifier limits here. We have a positive limit and a negative limit. That is the highest and low. Those are the highest and lowest voltages that our amplifier can supply. And in this example, then, we have our slope here. The slope of our amplifier represents our voltage gain. So if we look at a couple inputs, for example, we have one input here, input 1, which is a smaller sinusoid. The output from that would be this sinusoid shown on the right. We could have a second input, input 2 here, which would have a larger input, like this. And what you notice is that would create a large enough output that we actually couldn't, the amplifier can't create a high enough voltage given how large the input is. So the signal would go up and get cut off, or clipping, or clipped as they call it, on the positive half and also on the negative part of the waveform. So this would result in clipping or distortion. So that would, this is, when you turn up your car stereo really loud, this is the kind of distortion you would hear. It's called clipping. And so to avoid this situation, we need our voltage gain times the input voltage, in other words, the output voltage, this is V out, to be greater than L minus, right, this L minus, and we need it to be less than L plus, this positive voltage here, the maximum positive voltage. In other words, we can write that VI must be greater than or equal to L minus divided by AV, or less than or equal to L plus divided by AE, as shown in the bottom equation here. Now, a more typical, this, as I mentioned, this is a somewhat ideal description of the amplifier output because of how linear it is. A more typical characteristic, voltage transfer characteristic that we might see from an amplifier looks like this. And in this case, we see we have more of sort of this rounded behavior here, where it doesn't stop immediately, and we have a nice linear behavior here in the middle, and then it clips again at the top, but not quite so rigidly linear like in the previous slide. So what would happen then if we put the following input, the input on the left here, we had a sinusoid centered at 0 volts. What would happen is that it would try to amplify in this region of our voltage transfer characteristic, and you can see that that's perfectly flat, and as a result, we would get no output. Obviously, this is not working well as an amplifier, even though we appear to have a voltage transfer characteristic that gives us amplification. All right, let's do another example with this same amplifier. Now, in this case, we've decided, okay, well, we didn't get any amplification, so we're going to bump up our input signal significantly and make it much bigger on the input signal, but still centered at 0 volts. Now, we're only going to get amplification then in this region here, right? The only amplification is going to happen once the voltage starts to enter this region where the output voltage, where we generate an output voltage. So we're going to get amplification there, and so the result is we get this little blips from our input. Obviously, this is going to create significant distortion. The amplifier is going to work a little bit, but not very well. So how are we going to solve this problem here of amplification, where we get all this distortion, or in the previous example, no amplification at all? And the key here is something called biasing, and that is we add a DC offset to our signal. So instead of having it centered around 0 volts, we shift it over by some DC, right? This is called a bias voltage, or some DC voltage. And now our signal is centered around that bias voltage or DC voltage, and we try to center that, our input signal, so that it's centered right around this nice linear steep part of our voltage transfer characteristic. So in this case, we have a triangle wave coming in, and the output will be a nice amplified version of the input because it's following up and down on this voltage transfer characteristic. So if we look at the circuit symbol for this as shown on the right, we can see we have an input VI of t that represents the AC portion, this VI of t, but we also have a DC component to that called VI, and that is the DC or bias voltage that we need to center our input. So it's important to note that this AC signal is superimposed on top of the DC signal. And we can see that the output then also has a DC component V out and an AC component V out. In terms of labeling here, it's important to note that capital V represents the DC voltage, And so capital V, capital subscript here, lowercase v, lowercase subscript represents the AC component, and lowercase v, capital subscript represents combined AC plus DC. So you can see in this example here, we have lowercase v, capital O, that's the combined, and we have a DC component, which is capital V, and lowercase v, lowercase subscript, representing the AC component of the signal. Okay, and the last concept I want to go over in this lecture is another voltage transfer characteristic. And this time, the voltage transfer characteristic looks a little bit different. And the question is, does an amplifier that has this voltage transfer characteristic actually amplify it? Does it have gain? Well, the delta V out over delta VI in this case, so if we have some input signal, right, that moves this way, we get a big, so if we have a delta V in, we get a negative delta V out. So in this case, delta V out over delta V in is negative, but we still have gain. It's just that the gain is negative. This is not a problem at all. In fact, this is very common with transistor amplifiers. We will learn this later in the course, why transistor amplifiers tend to give us a negative gain. Now, if we wanted a positive gain out of this, we could cascade two negative gain amplifiers in a row, and we end up with a positive gain. All right, that is it for Lecture 8. Thank you very much.